Hi, I am Nafis Ahmed Ifti and my student ID is 2209061. In this video, I will present my final year project titled Adaptive Optimized Autoencoder with Calculus Guided Noise Suppression for Intelligent Image Compression. The aim of this project is to reduce the size of satellite images while maintaining high visual quality. This is important because satellite images require a large amount of storage and bandwidth, especially in real-world applications such as remote sensing and environmental monitoring. Now I will explain my system work. This diagram shows the overall pipeline of the system. The process begins with the input satellite image. First gradient analysis is applied, which measures how pixel intensity changes across the image. This helps identify edges and important structural regions. Then Laplacian analysis is used, which captures second-order changes in intensity. This is important because it helps distinguish between actual edges and noise, while gradient highlights where changes occur. Laplacian helps understand the nature of those changes. Using this information, a noise matrix is constructed. The matrix represents how much noise is present at each pixel. Based on this, a noise-aware processing step is a noise-aware preprocessing step is applied, where noisy regions are reduced while important features such as edges are preserved. Finally, the processed image is passed into the autoencoder model, where comparison and reconstruction take place. This pipeline improves the quality of the input before it reaches the neural network, which leads to better overall performance. Next, I will explain the neural network used in this project. The model is a CNN-based autoencoder, which consists of two main parts, one encoder and another one is decoder. The encoder takes the input images and extracts important features using convolution layers. It then compresses the image into a smaller representation called the latent space. This latent space contains only the most important information needed to reconstruct the image. The decoder takes the compressed representation and reconstructs the image back to its original size. The goal of the model is to minimize the difference between the original image and the reconstructed image. Now I will show the details layer structure. In this architecture, convolution layers are used to detect features such as edges, textures, and patterns. Max pooling is applied to reduce the spatial dimension of the image, which helps remove redundant information and reduce computation. During reconstruction, upsampling is used to increase the size of the feature maps. This allows the decoder to rebuild the image gradually. Together, these layers enable the model to compress and reconstruct image effectively. Now I will briefly show the implementation part of my dissertation. The model is implemented using TensorFlow and Keras. The dataset contains 1,423 satellite images, which are resized to 256 by 256 pixels and normalized before training. The dataset is split into training and validation sets to ensure proper evaluation. 20% of the real data used for validation and 80% from the real data used for training purpose. The model is trained using the ADAM optimizer, which helps update the weights efficiently and improves the reconstructed images and the real images accuracy. A batch size of 32 is used, meaning the model processes 32 images at a time. This helps maintain a balance between computational efficiency and learning stability. Now I will present the result of the system. Here is a table, it's called the benchmark table, where I explain between base model and the proposal model. The result shows that the proposed model improves performance compared to the baseline model, especially PSNR increased by approximately 1.44% and SSIM improved by about 1.21%. At the same time, reconstruction errors such as MAC and MAE reduced significantly. This indicates that the model produces more accurate and higher quality reconstructed images. Now I will show some output examples. Here we can see the comparison between original and reconstructed images. The constructed images preserved most of the important structures and spatial patterns, although some fine details are slightly reduced. The overall image quality remains high. Now I'll explain the main contribution of this project. The key contribution of this work is that I didn't modify the core neural network architecture. Instead, I improve the overall pipeline by integrating gradient and Laplacian-based preprocessing. This approach allows the model to focus more on important structural features, which reducing noise. As a result, measurable improvements were achieved in similarity and error metrics. This demonstrates that pipeline-level optimization can be an effective alternative to designing more complex models. Now I will briefly explain the code implementation of my project. First, I import the required libraries including TensorFlow, Keras, NumPy, OpenCV, and Matplotlib. Then satellite images are loaded, resized to 256 to 256 pixels and normalized to improve training stability. After preprocessing, the dataset is split into training and validation set. The CNN-based autoencoder is that defined. The encoder compresses the image into a latent representations, and the decoder reconstructs the image from the compressed data. The model is compiled using the Adam optimizer and then square error loss. I already explained the batch size and Adam optimizer, which is used during training. After training, the model reconstructs the test images and the outputs are evaluated using PSNR, SSIM, MSE, and MAE. In conclusion, this project shows that combining mathematical image processing with deep learning can improve image compression's performance while maintaining image quality. Thank you for watching this video.